Hello everyone, welcome up to the channel. Today we're going to speak about Semantic Version X. Semantic Version X is my implementation of Semantic Version X. It stands for Semantic Version Extended, based on the original specification and schema defined by the community, which is open source too. Semantic Version X really is a packaging system for versions, for libraries, for any library, for any component, based on that target language. It allows versioning. It extends the traditional major, minor patch systems with the standard schema configuration system. For example, it enhances developer integration from development to production. So you can for you think of each step: development, staging, testing, and production. These has to be handled in a coordinated way to deploy. So for each code base, a code name project like stable Scorpion, which is the stable division, stable code for the devs that are working on it, that actually push into the main branch in a GitHub repo or GitHub branch. The system allows you to define stable, legacy, and experimental components of that system to ensure that you get migration from stable to from the beta, which is just like a beta mail or beta system that's meant to be tested before it's shipped to the alpha, which is production ready. It's what based on quality assurance. You have to understand quality assurance is very key here. Quality assurance is a principle that states test-driven development, not the behavioral development, is used, not BDD but TDD, to ensure that each quality of the MVP or the prototype or the code can be migrated from the development to the production system for the real world consumption, to ensure there's no way to no faulty system that could reach issues in the community based on the foundation of that system. Semantic Version really uses a schema system for the polygons, and hybrid models to ensure consistency of behavior across various components. The Semantic Version X allows you to do a lot. npm install -g at obinexus slash SemVerX, which is just the extended npm version of Semantic Version, or the Python implementation, obinexus slash SemVerX. But you have to ensure hot-swappability of the component system, because for example, it uses step expression layers to hot swap systems. Hot swapping is just say you have one component like a whole entire package or library. It's now become a legacy component or legacy dependency. How do you resolve component dependency with SemVerX? Well, the answer, it's really simple to do all of this. SemVerX or Semantic Version X uses something called a Hamiltonian cycle. When you resolve a package using statement expression in 10 layers, where the statement is just a true or false value. Gets an output and there's no output. Is it this or is it this? Boolean based system for detecting yes or no values when a system is a state of yes or no. Or statement. Here's the statement. Expression means what's the result of that system, if it's valid, if it's invalid, based on the QA matrix. Quotations: true positive, false positive, true negative, false negative. And the intent is like how do I resolve this using a directed acyclic graph. Now the interior is very important to understand how this works. So in SemVerX exploitation, we have two main implementations. We have something called an Eulerian cycle. If you're familiar with graph theory, an Eulerian cycle is really a cycle where you can cycle that you visit all edges, but not relatively all the nodes of a graph, of a network. Because graph theory has nodes and edges. If you visit an edge, it doesn't mean you visit a node too. It's because you in continuous space, it doesn't mean you get to that node or get that information out of the system. But if so example, the thing is, so how this and the Hamiltonian cycle is really saying you visit all the nodes directly, all the artifact component. So we have like a kind of directed cyclic resolver between the Eulerian implementation of the packages and the system to resolve something before it's done. And that's how that works. is to mitigate something called diamond dependency problem. We have two libraries, library 2 and library 3 v1, where foo is just has a root variable, a root dependency, and foo has two dependencies, and then you store for 2, FOO2 in your system, version 2. That has to use the same interface or abstract class to connect in the diamond architecture. You, the consumer, try to consume the library, import foo into your program, say in Python, Node.js, Lua, but then the system doesn't know which to pick, leading to a catastrophic breakdown of the system's integrity, something known as decoherence of that system. Decoherence just means it's a fault when system decoherence, including libraries, component system, in the main program driver, means, for example, if you have a one dependency, another dependency, like a dependency A, used by dependency B, and C. So A uses B, and B uses, okay, C is using B, and B is using the A. So this is one dependency chain. But if system A, if dependency A, if dependency A degrades, then C will naturally degrade. Hence the same systematic degradation. Because degradation means if there's too much problems with system A, the library A, you already imported library A, you're trying to resolve to by library B. Now library A is using B, library B is using A, and library C is now using indirectly. It's not really making a direct call to A. It's using the interface of B to handle A. So that's system degradation. So that's the implement. So the first thing you gotta understand is diamond dependency problem, which is an anti-pattern, and the system decoherence pattern, which is also an anti-pattern, to resolve dependency hierarchical structures. For example, you have like so let's call the library a bar, and library B bars, and your program or library can be a program or library paths for C. So that's an anti-pattern. So path is now using B, bars and bar. But then if bar has an error, then bar will propagate that error to bars. And if bars has an error, it will then decohere bat, your program, or your library too. So that kind of things we're trying to resolve with the SemVerX problems, by giving this kind of architecture solution to it. I did mention intent layers and how they work now. I will mention now. So we have the intent layer really works in this way. We have the dependency to resolve, like so we have a dependency graph to resolve a system. But we have something called the Euler cycle. Now the Euler cycle is really flexible because it allows you to visit all edges but not all nodes. So we can check a system is available, has a component that we're missing, and hot swap that component being the library, respectively, without going through updating dependencies in real time based on the intent configuration or the configuration of that system. So for example, if you have three packages and three packages, A is connected to B, A is connected to B, B is connected to C. Okay, let me give you how this works. So the best way to understand this is using something called fault-tolerant topology. Fault-tolerant topology is a really concept. The simplest one is peer-to-peer networking. Peer-to-peer is like a server-client model. So, for example, your server, you have a server somewhere around the world. Your clients connect to it in a centralized fashion. You're the client, you're the peer-to-peer. Now, this is called a hybrid architecture because hybrid refers to the term that you have a server which have a task or role to serve clients, and the client is a consumer who uses that data to perform some computational resources thing. So or CDN. So how this works in this context is you have because this is a fault-tolerant system. It's first of all because this is a fault-tolerant system. It allows for mitigation of the grade and dependency hierarchy, and this is what the Euler cycle is really using. So, for example, this is the simplest model of a peer-to-peer network. or fault network topology, which we'll get into. But this concept is applied using a Eulerian graph structure. So for example, you have like a peer-to-peer system like this hybrid model. You then use the consumer, you make a request to a server. Your program makes a request to this server. It gets it. But then you see you get it and then resolve that answer. But you can say there's an error in the connection. You can request it again, or continue where you left off because the server knows how to continue with your request. Because that's what it's designed. In the root in production environment, in case of an exploit or something happens, it allows the system to heal itself. Other models of peer-to-peer encoder start where you have a centralized server, a centralized server S connected to like 4 nodes, 1, 2, or 5 nodes, like a start, like a hybrid 1, 2, 3, 4, 5 on the outskirts, borrow resources, which are clients. Now the clients can help each other with the services too, if they do have services. You got the bus topology. The bus topology is a hybrid model. It's more of a handling parallel and series connection in a way that's more orchestrated. Because you can have you can allocate jobs to them. But this is how the system works. Think of the parallel execution path as a way to get the bus topology to which is really flexible to perform some kind of job and prioritize jobs for a task to ensure the system is coherently doing a task, no matter the task. But it's really a networking concept. So I'm going to use the bus topology to give this analogy using the Eulerian and Hamiltonian graph structure. Eulerian graphs are, say you have a dependency version 1, and version 1 point, then you get version 2 using a major pass system, major minor pass. Again, you want to update to the later, you want to use the configuration system to update version 1 to version say you have version 1, then you want the latest major patch. So version 1.2 is the major, minor, and patch system. But now say you are, because it's now a legacy component in the stable region, in the stable code base. You want to update to the production ready in real time on the fly without getting involved in the code base. This can be automated easily by literally creating a computer system that allows dynamic updates with the root server, like a registry for a component. It doesn't have to be directly updated or shipped, or no downtime involved by the human to take down the server and put a maintenance page up. So since we have the schema version 1.4, which is now the new stable version, so that can be downstreamed. Version 1.4 is now the stable minor version. So what you're gonna do is update to version 1.4 without changing the full code base of the system. So how you do this is just literally allow the system to do it, having some kind of pattern recognizing system, or some kind of with some constraints to recognize which updates are good and which based on the code name, or like the long-term support or the experimental, if you're really confident, short-term support systems that may be experimental, maybe breaking changes, or maybe change the API behavior, which you're very careful of. But if you have a standardized schema for that program, this kind of registry, such as Python registry, PyPy, or my own registry, my own registry, Obinexus registry for components based on the monoglot, polyglot, and a hybrid system as channels to pull data from. So you gotta remember, mono stands for one language. Mono is one. GOT is one language. So if we have the schema at Obinexus slash which is a Python package. The schema follows at Obinexus slash SemVerX or .SemVerX, which is the external version you're pulling from. And then you get a .monoglot. The monoglot refers to just this program. This is Python monoglot. SemVerX. This is Python implementation. Now this monoglot refers to the layer of interaction. Monoglot is just where do I want my this is what kind of projects am I working on? Am I building just for myself, for business? Do I want to talk to other languages? We've got the hybrid model, which is like I want to talk some allow me to do it, but let me do it my way. It's really extension of the monoglot layer, but doesn't really enforce the polyglot aspect. You do the polyglot yourself. Connects to talk to any language however you see fit. It doesn't give you some strict constraint. And then you got the polyglot, which is many languages. I want to talk with the Obinexus registry or the PyPy registry that where there's a polyglot implementation, something known as foreign function standardized foreign function interface to the polyglot polymorphic function call library, function call like a function call library to interact with the main program to do it. So the monoglot locks you down into that language. The hybrid is what people will use most of the time. But the hybrid model allows you to talk to any languages without getting bogged down. For example, if you have a Python PyPy at Obinexus slash SemVerX in .SemVerX .monoglot, that's the schema or polyglot or ultimately at Obinexus slash pi0, which is zero no proof implementation .monoglot .hybrid .polyglot. You can use that to consume your code and deploy your app based on that configuration system from that Semantic Version X registry. So this is like a we can have like a SemVerX at v1 2. Okay, let me give you the full example now. So say I download this library with PyPy, Python -m pip pip will just package Python index package. Pip is an index command. PyPy on PyPy should deploy this. I install SemVerX, and then I have some SemVerX errors in my production. Now the filtering topology system uses a layering cycle to find the nearest neighbor using A star scoring. Like the nearest state dependency that's functional. If you want, you can really write a pre-processing script to run some mini stress, to enforce kind of some stress structure using some policy, which is just a wrapper decorated and enforces some logic based on some QM matrix in the layer. So, for example, if I download the SemVerX configuration system from Python, and then the Semantic Version X system then you're say using some kind of other library, you're building some kind of some kind of a Python library with some Semantic X using the setup the TOML configuration. You then have an update of that system of that library that you consume. Not like something like something more genuine, something like a Pygame. Let's say Pygame. You have a Pygame dependency update. You want to lock some dependency constraint. What you do is you use a DAG to find the nearest A star algorithm without touching all the nodes, touching all the edges to see whether there's an update to that node. Dynamically, where the nodes are really ambiguous, based on the Python Pygame schema, indirectly or directly, if you will, to see whether there's a Pygame update that gives you some feature or functionality that's been missing from the old version. Now, this Pygame example is really good because it shows how to introduce audio components or video components updates based on the graphical settings of that system. So that's what it is. Semantic Version X allows you to script updates the system on the fly, humans out of loop, no hands on the keyboard, based on the Semantic Version X of Pygame. So when you write Pygame, so you have a Python game now in the browser, you're really interacting indirect with the Eulerian graph. And then so you have those subcomponents as Eulerian filtering node graphs for the versioning schema, which extends to the X semantic versioning. But then for that semantic versioning, say you want to remove say something is faulty. Now you got Pygame audio, Pygame. Say you have a Pygame audio subcomponent, and it becomes legacy. It becomes incompatible, or you want to give your audience for this game, Python game you're making, a new feature. The 11th cycle now has to touch the Hamiltonian path. Again, using the A-star scoring algorithm to get the fastest path to the package. That's how that works. So the 11th cycle, or can use the bus topology or star topology or any fourth generation topology they can recover from the system, because from error based on how it's organized and configured. So the 11 cycles are really the configuration layers of how the program should find the update to Python, a Python subcomponent, a Python game subcomponent like an audio visualizer, a sound game for Lua, for any programming language. And the 11 cycle must resolve to a Hamiltonian cycle because there's an isomorphic relationship that exists between the data types based on the configuration. So when the Hamiltonian system, 11 system results as DAG of the subcomponents or finds an update to the video driver or rolls back based on the system you want to do based on intent layer, because you clap a version, you're not looking for updates based on the Python Pygame schema, how Pygame finds updates. You can automate this. The Hamiltonian cycle just says, okay, now I want to use this rotation, and I want to cache this rotation later in case I fall back to it. It allows you to resolve dependencies on the fly without actually interacting with it directly. Because you don't have to update it through one computer system. A lot of packages like such as Pygame, like Lua Love have a standardized way of shipping updates to a system. If you understand that, or if they lay out to you, if you look at that, you can find out for your use case, you can tailor it very specifically to your use case. And that's the beauty of Semantic Version X, hot-swappable component logic, an isolation of and able to isolate based on a Forte implementation of a separation of concern for heterogeneous. Heterogeneous refers to the mixed types of data that can be isomorphic but not be isomorphic, and homogeneous, similar types that reduce to isomorphic data structures that can be mapped around the schema standards by the library. For the anti-pattern dependency, diamond dependency problem, it ensures that you are updating what is needed, not what is just because it's not simple. It's semantic. You can really swap out whatever parts you use it for semantic version X and ensure that the structure remains intact with that Python version or that system you're using to ensure components are up to date and malware free without no downtime, which is what the hot-swappable logic is meant to be. For example, if I have a plane, a version, one plane, I want to put more people. I take out the seats and then take a new seat and put more seats in the plane, and vice versa. If I want to take out less seats, but if the wing is getting too, if I want to what we're doing, I don't dismantle the whole component or the whole library. I just take out the wings, bit in a way that's component driven. Take out the wings and then put the wings back in of that plane, and that plane will be able to still perform that job, but better. And that's the idea. You have a car, you take out the wheels for that terrain, and then that's the component law. It's not just all one monolithic system. It allows you to separate your concern to perform a task based on your feedback loop, the feedback loop you're getting from the real world, like an entropy check, and the system can grow and mature accordingly to Semantic Version X schemas. Okay, thank you very much. That is Semantic Version X in a nutshell. You can find it on github.com/SemVerX. But I'm working on the polyglot rotation to ensure that the hybrid system, the monoglot system, and the polyglot system remain intact when communicating seamlessly. I may write that in Rust, but thank you very much. And you guys see all the documentation on Gatebox. Thank you. Have a lovely day. Share, like, and subscribe to this video. And in the next video, I will literally show you maybe a drawing or a piece of code, some code for it, and many products.